go ahead and get started. Welcome to the first ever live Chase the Knowledge webinar. My name is Sherry Cudd. I'm the Advertising and Marketing Manager for Chase Plastics. We'd like to thank you all for your interest in this webinar and for taking time out of this beautiful day to learn about understanding plastic data sheets. So a few housekeeping items before we begin. Everyone except our presenters are on mute, and you will be for the duration of the webinar. But if you'd like to ask a question, you can do so at any time by typing it in the questions section of your toolbar. So if you look at your toolbar, you'll see a questions section there. If your question does not get answered right away, don't worry, we will address it at the end of the webinar. You can access and download PDF copies of this presentation and a sample data sheet located in the handout section of your toolbar during the presentation, but not after. So if this is information that you'll want to refer to, you'll want to click on the handout section, and there's two PDFs there. You'll want to download both of those. The webinar is an hour long, and we will conclude promptly at 3 p.m. Eastern Standard Time. A certificate of completion and a recording of the webinar will be emailed to you about an hour after the completion of the webinar. You will also receive a brief survey. We would greatly appreciate it if you could please complete the survey so that we can improve future webinars for you and our customers and cover the topics that are relevant to you. At this point, I'd like to hand it over to Jason Merkel. Jason is our technical manager, and I'm sure many of you have worked with Jason in the past. Jason?
Thanks, Sherry. Well, hello everyone, and welcome to, as Sherry mentioned, our very first virtual Chase the Knowledge event. As she said, my name is Jason Merkel, and I'm the technical manager for Chase Plastics. We put together the Chase the Knowledge platform several years ago as a way to help educate our customers on various aspects of the plastics technical world. Traditionally, we've given these presentations in person, but we're happy to present to you virtually today. Here at Chase, we strive to be a materials and processing consultant just as much as a resin distribution company. Our team of technical development engineers is standing by to help with any of your product selection, design, testing, or troubleshooting needs. We come from a variety of technical plastics backgrounds and levels of experience and welcome the opportunity to provide insight on any of your projects or problems, whether they be large or small. I hope you find today's presentation helpful in understanding the benefits and limitations that come with interpreting a plastics material data sheet. We'll be sure to follow up with other Chase the Knowledge events in the future on other technical topics as well. So without further ado, I'd like to introduce Andrea Kendrick, Technical Development Engineer with Chase Plastics. Andrea is based out of our Clarkston, Michigan headquarters and supports several regions with technical service and application development efforts. Andrea has her bachelor's degree in plastics engineering technology from Ferris State University, and she's been with Chase Plastics for 5 years. Andrea, take it away.
Good evening, everyone. I hope everyone's doing well. And without further ado, I'm going to go ahead and get started. So our agenda for today, we're going to go over what exactly a plastic data sheet is if you've not seen one. We're going to go over differences between data sheets and graphs, some limitations of data sheets, and then we're going to spend some time going over different test methods and test properties from each of the different categories that you see on the screen. Also a little bit of kind of housekeeping, if you will. There are some pages that you'll see as we go through. They're known as quick explanation pages. I'm going to kind of gloss over those rather quickly. I want to spend the majority of the time on the tests that you're going to see more readily, but just know that they're on there for you to reference back if you want to learn a little more about those. So what is a plastic data sheet? Sometimes they're also known as technical data sheets, TDS. For the remainder of this presentation, you'll see TDS referenced quite a bit. But essentially, they're a marketing tool. They give you a snapshot of short-term performance. They give you course comparison between different resins and compounds. So if you're looking at two different data sheets to compare. But do note that these collections of properties are done at one distinct set of conditions and variables. So when you're looking to compare the different tests, the different properties, just note that they could have been conducted at different conditions, and that's something you should be aware of when you're looking at it. And then if you see over here on the side, there is a data sheet that we put in here. We also have the Altem data sheet as a handout that you can download. I would advise you to do so if you want to follow along. I will occasionally reference it during my presentation. So what do we want to look at first? So kind of when you first get a data sheet, you've never looked at one before, what am I supposed to do with this? So the first thing you're going to want to do is you're going to look at some general properties that are specific to that type of resin. So if you're looking at maybe an ABS material, the first thing you might want to look at is the different impacts. They span from, just a general purpose impact to maybe a high impact grade. So something to consider when you're looking at it. Or if you're looking at a TPE, you might want to look at the hardness because that's going to be a specific type of test that's unique to that resin. So you're going to want to look at that first. And then some other ones to look at: specific gravity, melt flow, strength and modulus, and HDT for some thermal performance. These will give you a real good idea, if you look just those properties first, of kind of where this material starts to fall, to then you can compare it to other ones. So if I'm looking at a particular data sheet and I'm looking to compare it to another one or maybe find an offset, these are going to be some of the things I look at first when I'm trying to determine what I would use as an offset. Data sheets versus graphs. So as we mentioned, data sheets, they're a snapshot of properties. There's only one set of conditions and variables it's being tested at. Now that's different from a graph because a graph is going to be a response to changing conditions. So you'll see over here on this graph, you have the stress and you have the strain information. So you can see across different strains, the different stress that you're seeing. With this information, you're allowed to do things like interpolate. So if I'm looking at this particular graph, I see a 0.02 value, a 0.04 value, but maybe for my particular application, I need 0.03. I can go through here and I can go up the line and I can see where those values are going to be at based on a graph. If I'm looking at a data sheet and it only gives me the 0.02 and the 0.04 values, I could maybe guess, but I'm not going to know for sure what's happening in between those different data points. And then the other thing you can do is extrapolate. So what's going to happen at the end of this graph? If my value that on my data sheet only goes to 0.12, what happens after that? If I'm looking at a graph, I can see this starts to dip and it's going to fall off. I wouldn't necessarily know that looking just at the data on a data sheet. So kind of alluding to this a little bit, some of the things to be aware of when you're looking at data sheets, again, apart from maybe just being the one condition, the one variable, some other things to note when you're looking for particular materials is to understand that the environment your part's going to see could also affect how they're going to perform. What kind of chemical environment are you seeing? Are you dealing with chemicals that could be detrimental to the material that you're using? Is it going to dissolve it, or is it going to alter it in some way? Maybe it's going to swell. It's something to consider when you're looking at that. So the properties are fine on the data sheet, but if it's seeing something that's aggressive towards it, it might not perform the way that you're expecting it to based on the data sheet values. And some other things that are similar to that would be your thermal exposure. If I'm looking at a property for tensile at room temperature, which is how it's going to be tested in a lab, 73 degrees, but your application is going to be at 100 degrees, there's going to be a different level of performance expected. So just keep that in mind. Same with UV exposure, humidity for materials that are affected by that, your nylon, your PBTs, how's that going to affect it if it's seeing a lot of humidity in application? And then some other things, some part design, some processing. If you're designing it, it's got maybe some sharp corners or the wall is not thick enough, that's going to affect how it's going to perform based on expectations you might have on the data sheet. And then processing as well. If you're molding it maybe too cold, it's got molded in stress, it could be a problem. So it's just some things to keep in mind as well when you're looking at data sheets. They give you a good idea of kind of how they're going to perform, but also note there's other variables that are going to affect it. So now we'll get into the property category section. If you do happen to have the ULTEM datasheet open, you'll see that there's different headers, physical, mechanical, and they kind of go down the row like that. So these are how we group our different properties, the main ones being physical, mechanical, impact, thermal, electrical, flammability, and optical. And so if you're looking again at the ULTEM one, they touch on pretty much all of those on their data sheet. And then now we'll start getting into some of the tests and the specific properties you're going to see under each of the categories. So we're going to start with our physical properties. And then just note that all of these slides are formatted pretty much the same. You're going to have your test method up first. I'm not going to touch on those. You can kind of read them or see them. The units, so how is the value on your data sheet? What are the units for that? And then we're going to define it, and we're going to give kind of some application to how that works in the real world application. What does that mean to us when we're looking at that property? So the first one we're going to look at is going to be specific gravity. Sometimes you'll see they just call it density, but just note that specific gravity itself is the ratio of the material's density compared to the density of water. So what does that mean to us? A few different things. One, if you have a material that's heavier than 1 gram per centimeter cubed, it's gonna sink. So it's heavier than water. It's going to sink when you put it in water. If it's less than 1 gram per centimeter cubed, it's actually going to float. So that's one thing. If you've got maybe some unfilled propylene, polyethylene sitting around, knowing that it's got a density of less than 1, if you throw it in water, it should float. Could be a quick check to make sure that's, that's what you're getting. The other thing to consider is that with a consistent volume for your part, based on these different specific gravities, your parts are going to weigh more or less. So I gave a quick example down here, ABS at 1.05 and polypropylene at 0.902. So again, keeping going with that, what does that really mean to us? Plastic pellets are sold per pound. We're not selling them on volume. So just note that if you get the same bag weight, a 55-pound bag, you're going to be able to make more parts out of lighter materials than you are out of heavier materials. So a quick little math here for you guys. If our part is 100 centimeters cubed in volume, and we use the same example as the last slide, your ABS and your propylene, if you get a 55-pound bag of ABS and a 55-pound of polypropylene, you'd roughly be able to make these many amounts of parts. So for ABS with that weight and specific gravity, you'd be able to make roughly 237 parts. Now with propylene, as we mentioned, lighter materials, you can make more parts. Propylene is lighter than the ABS. You're able to make roughly 276 parts. So we haven't even discussed the difference in cost, but alone, just because of the weight and specific gravity of these materials, you're able to get different amounts of parts. So again, another thing to consider if you're looking at two different materials and the costs are way different, also consider that it might be because one's lighter or heavier, you're going to get more out of it than the other. So another thing, again, to consider when you're looking at pricing instead of just the price, a little bit more to look at. So next we're going to talk about shrinkage. You'll either see it inch per inch, sometimes you see it in percentage, but essentially it's the dimensional difference between the molded part and then the actual mold dimensions as a result of the polymer chains contracting upon cooling. So materials expand when they get hot and then they contract when they cool. So that's known as shrinkage. So just note that all plastics are going to shrink. It's what they do, but not always by the same amount. Your semi-crystalline materials that are more crystalline, they have to expand more to be molded. They're going to shrink more. Compared to your more amorphous materials, your ABSs, your PCs. So just note also that some data sheets and some suppliers will give you shrinkage values on their data sheets. They're really good guidelines, but also note that things like your gate geometry, your gate location, number of gates, dimensions, how you're going to process, these all can affect how it's going to shrink. So again, real good guidelines to start, but just know that you might get a slightly different value than what's shown because of those different variables. So when you're looking at a data sheet, when they give you the shrinkage values, depending on if you're doing ASTM or ISO method, here are the different plaques that they will mold and then determine shrinkage off of that. So again, if you have a pretty complex part, if you're basing your shrinkage off of that little square that you see there, it's only going to be so close. You still have a complex part that you have to work with. And the other thing that I wanted to note here is if you're looking at this picture over here on the right, you'll see that you have flow direction. So here's your gate, the material's gonna flow in this direction. That's why they call it the flow direction. And then you have the transverse direction. Sometimes you'll see parallel and perpendicular. Those values are used, flow or transverse. Those are to let you know in what direction they're measuring the shrinkage, because sometimes you'll get both flow and transverse on there. So you wanna know kind of what does that mean exactly. So now let's move on. Physical properties for melt flow and melt volume rate. This essentially is the extrusion rate at which the resin is going to go through an orifice at defined dimensions at specific temperature and load. So those values are polymer specific. Obviously, you have to get to the right temperature. If it's a higher heat material, it's got to get to the right temperature to flow. So just make sure you're looking at those conditions. Some materials have a lot of different options, like your ABS. There's 3 main different temperature and load variables. So just make sure when you're comparing them on a data sheet, you're really looking at that to show that. So what do we use this for? It can be used to differentiate different grades and of the same material. It can also be used as a measure of degradation of a material as a result of molding. So I want to take a step back. So within the same material, if I'm looking at melt, I'm only wanting to do it with materials that are the same. I'm not going to take a 20 melt PC and compare it to a 20 melt ABS because they're going to react differently under the shear rate that is put on it during injection molding. So these are a very low shear test. So it's not necessarily indicative of what's going to happen during processing. So a PC is going to react differently and push harder than your ABS. So 20 melts are not going to be the same when you go to process them. However, if you're looking at them, you got a 20 melt ABS and it's flowing okay, but you need a little bit better, you might ask for a higher flow ABS. Again, not exactly how it's going to work in the injection molding machine, but you do know that the higher melt is going to flow easier. So something that you can look for if you're molding them apart and you're having some trouble. The other thing to note is that your melt flow rates and melt volume rates, they're very affected by moisture in the material. So that's why you'll see materials like nylons or polyesters, PBTs, they're not going to have melt flow necessarily on them or on the data sheet or as a test, because even the slight difference in decimal percentage moisture is going to highly affect the melt flow rate you're going to get. It's going to flow a lot easier the more moisture it has. So it's hard to use that as a way to define it. So there's other melt testing that can be done for those types of materials, but just note you're not going to find them on the data sheets. So what does that look like? So if you look over here on the left-hand side, you'll see what the tester looks like when we're doing melt flow. So over here, so you got your loads on here, and then this is where it heats up and the material's in. And so look on the inside, here's your load. So whatever the load is on the second half of your conditions, and then this heats up to the temperature that's given. So like I mentioned, a lot of different materials, a lot of different conditions. Your conditions, just for some standard ones, are given over here. Your temperature, 200 C, and then 5 kg. And so there's different ones for each different material. If you're looking at the data sheet for the Ultem material, you'll note that the melt flow is done at 337 C, so much hotter, and 6.6 kg, so kind of an odd weight. But again, if you're trying to compare it to a similar material, make sure that the conditions are the same. And then another quick one, so I keep saying melt flow rate and melt volume rate, they are a little different. Your melt volume rate is going to be the volume displacement during the test. So if I start up here for my test and then I end up down here, this section right here, all this volume that was displaced, that's going to be the value that's given. Your melt flow rate is exactly the amount of material that comes out, and they weigh it. So your grams per 10 minutes. So this material coming out here, it's going to come out, they're going to weigh it, grams per 10 minutes, that's your melt flow. Melt volume, here's the displacement in volume during the test. So if you see them, you can compare them. You'll need your melt density of the material because obviously it's molten, so it needs to be in molten form when you're doing it. You can compare them, but just know that, again, it's another thing where they're slightly different, something to catch if you're looking at data sheets and you're trying to compare. So here's one of the first quick explanation pages I mentioned. I'm not going to go over them too much. Just know that there's water absorption in here, information on that, and outdoor suitability is also on here. So I'm going to go over that, but again, you can look at it at later time when you're reviewing the presentation. So now we're going to start getting into our mechanical properties, our tensile modulus. This is the ratio of tensile stress to tensile strain of a material in the elastic region of the stress strain curve. So what does that mean exactly? What is modulus? Modulus essentially is the resistance to deformation under load. So if I take a part and I'm pulling it at the ends, how much is it resisting me pulling that and trying to pull it apart? Some other terms you might have heard of: Young's modulus, modulus of elasticity. Those are other terms that we use for tensile modulus. So if you're seeing that, or you're doing maybe some FEA work or stuff of that nature, you might see that those values are asked for. Just know that that references tensile modulus. And then also you'll notice we'll also talk about flex mod. Just note that really the difference is how it's being put into stress. So for tensile, you're pulling it apart. So I'm pulling it in this direction. I'm pulling it apart. So now tensile strength, it's done in the same apparatus. It can be taken from the same test, but essentially this is how much load can it take before it breaks? How much can I pull it apart by how much stress before it finally breaks? So a couple of different ways that this are tested. If you're looking at data sheet, they might say something like yield or it breaks. So just know that tensile strength is tested to break, either point of rupture, so I completely broke it, to yield, which is when you have an increase in strain, it no longer results in an increase in stress. I'll show you what that looks like on a graph later. Or ultimate, which is really just the highest stress that material can support before it's going to fail. So if you're looking at this picture now, this is what the test is. You'll have a part that's put in there, right here in this area. So it's put here, it's clipped here, and then they pull it apart. So your strength is going to be how much load did it take before it pulled apart. And so this is what it looks like when you actually do the testing for that material. And then if you're looking at the Ultem test, you can see that they have tensile strength at yield. So just note that that's at yield, not at break, but also some will be at break. So again, you want to compare similar conditions. And so what does it look like? Kind of a lot going on here, but there's a couple graphs so you can kind of see where the different points are. So your yield is going to be over here in this area where you have the little hump and then it stops increasing. Same over here, your yield at these, and then your break where it completely snaps and breaks off. So these are going to be where your values and what they look like on a graph when tested. Tensile elongation, again, same test as tensile strength and tensile modulus, all from the same apparatus. It's essentially a measure of the change in size versus the original size as I'm pulling it. So it starts at whatever length it was, and then where it ends, what was my percentage of change. And so something to consider if you're thinking about it and you're like, what does that really mean? If I take paper and I'm trying to pull it apart, if you have it in your hands and you're just trying to pull it in opposite direction in tension, it's going to rip, it's going to tear. It does not elongate at all. If I take something like a Laffy Taffy, grab it from the ends and I pull it, it's going to elongate quite a bit before breaking. And so similar concept too, you can also do it at yield and break. It'll take the measurement at those specific locations. If you are looking, again, Ultem 1000, it's done at yield and at break. So there's two very different percentages there. It's only 7% at yield and 60% at break. So again, if you're comparing, just make sure you're looking at the same property and the same condition. So flex modulus, so similar concept to your tensile modulus, it's going to be the resistance to deforming. But in this case, and for flexural stuff, it's going to be bending. So I'm pushing down in this direction. So instead of pulling it apart like you do for tension, flex, I'm pushing down in this, right in the middle of a beam. And so that's going to be what your flex mod is. So the other thing to think of is if maybe if you take a pencil in your hand, if you're taking notes right now and you're trying to bend it, like at the middle, if you're trying to bend it. So that's going to be what we think of stiffness. So how much does it resist wanting to move? That's when I say stiffness. So if someone says, you know, I need a stiffer material, you're probably looking at your flex mod. That's how much it's resisting deforming. So also same concept, there's also flexural strength, difference being how is it being forced? What kind of force are we putting on it? For your flexural strength, we're pushing down again in the center instead of pulling at the ends like you do for tension. And so this, same as tensile strength, it's how much force is it going to take before it's going to break. Hardness, this is something more common for your soft touch materials, your TPEs, TPVs, stuff of that nature. Sometimes you'll see it on harder materials, but they're generally in a different unit than Shore A or Shore D. They're either Rockwell, you know, R, M. There's a few different versions of it, but if you're looking at a TPE, this is what you're going to see most commonly is your Shore A or Shore D. Essentially, hardness is a measure of indentation resistance of the elastomeric or soft plastic material based on the depth of penetration of the indicator. So if I'm thinking about this in practical sense, if I take a soft touch material and I try to dig my fingernail into it, I just push down, how much does it resist me pushing down? The harder the material, the harder it is for you to push your fingernail into it. The softer, the easier it is. And so when I'm looking at the different units, durometer A typically, not always, but typically is used when we measure materials that are less than or equal to 90A in durometer. We do have a couple grades where we might go a little bit harder for that and still measure. Like we have a 95 AB Avalon TPU. But typically, once you start getting that hard, then we move over to the Shore D. And so harder materials are Shore D of greater than or equal to 20. And so what does that look like? Why do we have the different ones? It all comes down to the different type of point they use when they're doing the testing. So your Shore A for the soft material is more of a blunt point. There's a little bit of an end to it, whereas your harder materials, your Shore D, are done with more of an actual point. So it's going to resist it a little bit less when it's coming at a sharper point when you're doing the testing. So just know when you see the different values, it's just because it's tested with a different probe tip. So what does that look like for different materials? Where do they kind of fall? This is a really good graph to show you of the different materials that are kind of out there. Where's their typical range for hardness? Where do we typically fall? So you'll see at the top your COPEs, your key flex type materials, your EVAs, your TPUs, your TPVs, your SARlinks, TPEs, Telcars, thermalast grades. So where they fall on the scale, and you can see that there is overlap between the two. You have your A scale here, and so you can see your TPs get pretty soft, and then your D scale, where your key flexes of the world, a little bit harder material, and then your rigioplastic, so your standard nylons, ABSs, much harder than your TPEs. And then for reference, I did include this graph here, or bar chart, if you will, of the different durometers and the different Rockwell hardnesses of your standard materials. So you'll see acetal's up first, there's nylon on there. It kind of gives you a nice little range where they tend to fall for their hardnesses. So you can get an idea of what's a softer or harder material. So just, it's in there for your guys' reference. Next, we'll start talking about impact properties. So your impact properties are standardly Sharpie and IZOD. So IZOD will be the one that we talk about first. What does IZOD mean? It's the energy per unit thickness or area, depending on the testing, we'll get into that, required to break a test specimen under flexural impact. So it's held vertical in a cantilevered beam, which I'll show you the pictures down below, you can see them, and then it's impacted by a swinging pendulum. So the energy lost by the pendulum is what they use to equate to the energy absorbed by the test specimen, so how much energy did it take to break it. And so the reason we say unit thickness or unit area is because depending on if we're doing ASTM or ISO, it's going to be a different value. So ASTM, when you're looking at them, tests are done by thickness. That's why you'll see foot-pounds per inch on the data sheet. Whereas if you're looking at ISO testing, it's done by area, so foot-pounds per inches squared. So just note that they are different. So if you're looking at them and you're like, man, this one's really high for this test method for your ISO, and you're like, man, this is like double what this ASTM is, just note that it could be that the values are different. One's done in thickness, one's done in area. And so for the test itself, the big difference between your Sharpie and IZOD is going to be how the part is held and how it's impacted. So this is what it looks like. It's being held in a device here, and the pendulum will come down and hit it. On the next slide, I have another picture for you. And that's going to be different than your Sharpie, which we'll talk about after. So if you're looking at the part again, this is the overall test apparatus. Some of them are a lot bigger and a little more complicated now, but it gives you an idea. Here's your pendulum up here with the hammer. It comes down, and then you'll see the part standing up right here. When it drops, it hits it, and then it takes the energy it was required to break that. And so if you're looking directly at the part itself, it's being held, pendulum comes down, hits it, gives you the value. So that's for your IZOD. For Sharpie, like I mentioned, similar, it's still impact, but it's held differently in the apparatus. And so same concept, unit thickness or area depending, ASTM or ISO, but instead of being cantilevered and held up, it's on a simply supported beam. And then the pendulum comes through and hits it right here. So what does that look like? Again, your part's here. You have the whole piece, your hammer comes down, but instead of being held upright like IZOD, Sharpie is held across like this. So it comes down and hits it. And so we sometimes get the question because we're comparing data sheets and you've got one that has IZOD and one that has Sharpie, and people want to know, hey, can I compare them? The answer is there's no real way to convert them or to get them maybe into the same to where we can compare them across. Generally speaking, they tend to kind of run hand in hand. You're not going to get a 5 IZOD material and a 40 Sharpie material for values, but there is no way to really compare them. You're going to want to do, Sharpie to Sharpie or IZOD to IZOD, but they tend to run kind of hand in hand. So you might have one that's a 5 IZOD and maybe a 6 Sharpie. So it'll be pretty close. Again, we cannot compare them. So we're going to want to try to compare the exact tests to the exact tests. The other thing to note there are sometimes where they'll test it as an unnotched version. So if you're looking at this picture right here of the Sharpie specimen, you'll see this notch right here. So this is when they say it's a notched Sharpie or notched IZOD. It's really when they put a notch in it. So they cut out this little triangular section to allow it for the impact to propagate right across that area. That's really what starts at. And so if you're looking at a data sheet that says unnotched, essentially what that means is this just isn't here. It's just a rectangular piece that they're trying to break. So just note again, another condition to be aware of, they're a little bit different. So now we'll start talking about some thermal properties, starting with heat deflection temperature. Real scientific term for it, it's when it deflects 10 thou inch when it's loaded at 3-point bending, specific outer fiber stress. So you'll see on a data sheet, there's generally 2 different conditions, either 66 PSI or 264 PSI, also known as 0.45 MPa or 1.2 MPa. So the different loadings are the different conditions for this particular test. This is also known as heat deflection under load. So if you see DTUL or it's referenced somewhere, just note it's the same test, just has an updated name for it. And then deflection temperature, it's a real good use for short-term heat resistance. So if I put a load on it and what it does is it slowly temperature rises, and then eventually when it deflects that 10 thou, it's going to take that temperature reading, and that's the HDT value for that material. So I know for a good short-term heat resistance performance, if I'm utilizing a temperature that's quite a bit below HDT, I can go, I'm probably really good to be at that temperature. If I'm looking at something above it, So for instance, your Ultem 1000, the HDT on this particular grade is either 201 if you're looking at the 1.8 MPa value, or 210 C. So if I'm looking at something where it's gonna maybe be under a little bit of load, maybe a little bit impact, at 250 C, I'm gonna go, this Ultem grade is no good for that. It's not gonna withstand that. It's not gonna be able to handle that temperature that we're looking at. Now, if they come to me and they're saying it's, only gonna maybe see 100 C, I can go, for short term, this is definitely gonna pass that. It's gonna be no problem. So just note it's a short term, it's not a long term. Also, so if I'm using it consistently at a certain temperature at 201 C, it's something we need to look at maybe outside of HDT. It's just a quick little, this is going to deflect at this temperature, so be aware of that. So what does that look like in a machine itself? So when you have your little part here, so this is your plastic bar, the load's put up here. So again, either the 66 or the 264, and then you have the thermometer. It's slowly raising the temperature. Once it deflects, it's going to take the temperature. That's the value that you're given. So that's how you do your HDT testing. And then the other thing to note is a lot of times, and we have had people ask for HDT on maybe some of your softer materials, your TPEs. The reason we can't do that is because as soon as you put a load on it, it's going to deflect. So the oil at room temperature is just going to show as the value. So I have had people in the past ask for HDT on TPE materials. We're not able to do that because it's automatically going to deflect. It's a soft material. It's not going to resist bending. So just note that that's something we don't typically see on your TPE materials. Relative thermal index, RTI, this one's a little different because this is done through UL, but something you're definitely going to see on your materials data sheets if they have this rating. RTI is an indication of material's ability to retain a particular property. So if you're looking at the RTIs, it's either physical, mechanical, electrical, or impact is the standard ones. When exposed to an elevated temperature for an extended period of time. Essentially, this is a measure of the material's thermal endurance. And so what does that mean and what does long time mean? The temperature rating given, so if we're looking at the Ultem, we're looking at values of 170 C across the board. It means that for 100,000 hours, or 11.4 years if you want to do the quick math, at that temperature, when I test before I expose it, I test the electrical properties, the impact properties, and the strength properties, I can leave that material at the 170 C for 11.4 years, and when I test it at the end of it, it's still going to maintain at least 50% of those values. So whatever the starting value was, put at that temperature for that extended period of time, it's going to be at least half that at the end of it. The other thing to note, and it happens quite a bit, is that sometimes the suppliers won't have the RTI tested for their particular materials, so they are able to be given a generic rating based on that type of material. So if I took this Ultem and they didn't want to have it tested specifically and pay for the testing because it's very expensive, it takes a long time, about 2 years, can cost hundreds of thousands of dollars to have the testing done, they can be given a generic rating. So what does that look like specifically? For different materials based on UL testing, these would be the standard values it could be given if you don't want to do the testing. So if we're looking at the PEI value, which is your Ultem, the generic value is 105. So this Ultem 1000, you can tell, was in fact tested because it was not given the generic 105. It was much higher than that. So sometimes you'll see when you're looking up certain materials, their RTIs are all the same. They're all the 65 for the nylon or the 80 for the PC. It's just because they decided to go with the generic value instead of having that particular material tested. Because again, expensive, very long time. So, and then these are a majority of them, and then the ones that you don't see on here, the majority of them will be tested at 50 C. And so not all of them, but the majority of the ones that are not on here will get a generic rating of 50 C. But these are some of your higher temperature ones that you can look through. Some quick explanations for thermal properties, going over VICAT softening and CLTE. I'm not going to spend too much time, so I can focus on the other ones, but again, in here, if you guys want to review after the fact. Also, thermal conductivity is in here. One thing to note, that the conduit line from SABIC LNP is in here. So to give you an idea of it, as you probably know, plastics are insulative, both thermally and electrically. And so we have to do something special to it to get it to actually conduct the heat. So there are grades out there that are good for heat sinks and stuff. So we do have special grades that are like that if you need it. Next, we'll get into some electrical properties. I wanted to spend a little bit of time on resistivity because there's a lot that goes behind that unless you're working in it, maybe you're not so familiar with it. So resistivity, what does it really mean? It's resistance to leakage current through the body or along the surface of an insulating material. So surface resistivity would be the leakage through the surface, and volume resistivity would be through the body of the part. So it just depends on how you're testing it if you're looking at surface or volume resistivity values. So kind of like we mentioned, plastics, they're inherently insulative. They don't want to conduct any of it. And so their values tend to be in 10 to the 13 ohms plus. So they're not going to conduct it easily. They're going to resist conducting it, so the value's higher. So what does that mean, being insulative? It means they're going to prevent or limit the flow of the electrons across their surface or through their volume or body of the part. So that means if there's a static charge, it's going to remain on place on the plastic itself. So if you've ever had one of those little slides that the kids would play on and you walk over and there's a lot of static flying around, you touch it, it's the static charges on that surface, it zaps you, you get a zap. So that's kind of what that means and what that's like in real life. So although they are inherently insulative, we can add things to them to adjust that. So we could add additives, sometimes we'll do coatings, you could add conductive carbon black, carbon fibers, different metal fibers, because metals are conductive, they will conduct the electricity a lot easier. So we can add those to our plastics to get them to start to conduct and reach different resistivity levels for different types of things. And so there's a range of materials. They're called electrostatic dissipative materials or electrostatic dissipative protective materials, so ESD. So sometimes you'll see or be asked for ESD materials. So that is a range of materials and different values. There's actually 3 within that range. We'll go over in the next slide of values and what each one does in that value range. So for ESD protecting materials, you have 3 different ones: anti-static, static dissipative, and conductive. So your anti-static materials are going to be in your 10 to the 9th to 10 to the 12th range. If you remember, we mentioned the insulative ones are going to be 10 to the 12th, 10 to the 13th, and up for standard plastic, so they don't add anything. And so what does that mean in the anti-stat range? What is that going to do for my part? It's going to suppress the initial charges. So it's not going to, it's going to stop them. And it's also going to stop the buildup of static electricity. So if you're worried about stuff like dust collecting, or maybe you have a couple totes and they're sticking to one another, you could add an anti-stat additive to prevent that, to stop that from happening. Then the next range would be your static dissipative. So this is going to be your 10 to the 6th to 10 to the 9th range. So this is going to have low or no initial charges, and it's going to prevent the discharge to and from human contact. It will ground a charge. It's just going to do it much slower than a conductive grade. So this is going to be good for limiting the charges. It's also going to prevent your discharge. So it's not going to, shock, if you will, or give the discharge onto a human being if they're touching it. And then your last one would be your conductive. So this is less than 10 to the 6th, so much lower resistivity. There's going to be no initial charges, and it's going to provide a path for the electrons to freely flow across the surface or through the bulk of these materials, making it easy to ground them or move them to another conductive material. So if I need to move the charge from one material or one part to another, I would look at a conductive material. This is what your standard metals would do. And so we would add, maybe stainless steel or carbon fibers to our plastics to get in those range to be able to do that as well. And so just note that we've been asked in the past, someone will say, hey, I need an ESD material, and we go, awesome, I need a little more than that, because there are 3 different ranges within that. So just note that we'll want to understand what they're trying to do, or maybe what range they're trying to be in when they ask for that. So that's some of the questions we'll ask if asked about ESD materials. Another couple quick explanations: dielectric strength, dielectric constant. Both are in here for you guys just to review later. Just quick definitions and some test methods for you. This one, another quick explanation, I won't spend too much time. The one thing I did want to bring up on this one particularly is going to be the PLC, your performance level categories. This is something that you'll see a lot if you're looking at a UL yellow card. You'll see PLC of 0, 1, 2, 3, whatever have you. So really what that takes is, instead of having, in this particular case for arc resistance, instead of spelling out the exact second or second range you'd like it to be in, you can just give it a simple number, 0 through 7. So if I need it to perform for this particular test the resistance is going to be maybe 325 seconds or 359 seconds. I would just give a PLC of 2 or less. The lower the value for PLC, the better performing it is. So in this case, it's resisting the arc for 420 or longer at 0. And so I just wanted to bring that up because you'll see stuff, your CTIs, your HAIs, your HWIs, they will have PLC values. So I wanted to bring up kind of what that means and what to look for in that. And again, the lower the number, the better performing. So if you're looking for a value of 1 and the material that is being suggested or looked at has a value of 0, it means it performs better than what you're looking for specifically. Now we'll start to talk about flammability a little bit. Limiting oxygen index, LOI. This is essentially the amount of oxygen that's going to be needed to support flaming combustion in a flowing mixture of oxygen and nitrogen. So how much oxygen needs to be present for this material to continue to burn if lit on fire. So the value can also be used just quickly to determine if material itself is going to be self-extinguishing or if it's to be one that continues to burn and support open air burning. So we're going to probably have to add some type of flame retardant package if we don't want it to continue to burn. So on average, we like to say that there's about 21% oxygen in the air. So anything that is less than or equal to 21%, so the value of 21 or lower, it's going to support open air burning. Because if you're looking at a grade and the LOI is 14, it only needs 14% to continue to burn. If we've got 21% in the air, it's going to keep burning. And a general rule of thumb is if you're over 30%, it's considered self-extinguishing. So it needs quite a bit of oxygen in that area to allow it to continue to burn. So for a good reference, this graph kind of gives you an idea of where the different LOIs are for different materials. So some of you that know already, your PEIs, Ultems, your PPSs, they are well above the 40 and the 40 range. And so they're considered self-extinguishing. We don't have to add anything to them for them to stop the burning. And then some of your other materials that are here below the 30 range, they can be FR and they will stop burning, but something has to be added to them to get there. And so your ABSs, you have to have a flame package. Your nylons, you have to have a flame package. One thing to note, your acetal, this one way down here, there really isn't anything you can add to acetal that's going to allow it to be considered an FR material, something that will stop the burning. So just note that we have in the past maybe been asked for an FR POM. They don't exist. The best you're going to be able to do is about an HB rating, which we'll get into the ratings a little bit later. But just note these ones down here that need very little oxygen to continue to burn, they're more difficult to get them to self-extinguish and to meet FR requirements. And so we talked about HB a little bit, so let's maybe dive into that a little bit for your flame ratings. So this is through UL 94, similar to your RTIs, also a UL test. So what do these all mean? They're flame and burn tests conducted on materials under specific conditions to compare them to relative burn characteristics of those materials. So you'll see a whole bunch of them spanning from HB to 5VA, 5VB on data sheets. So for each particular one, there's different circumstances in which you'll test it. And then there's different criteria that needs to meet to get those ratings. So your HB from the ever clever UL is horizontal burn. So we'll burn it horizontally. It's one of the least stringent tests that you're going to see on there. And then you have your V0, V1, V2. So V for vertical, also very clever for that one. They're more demanding than your HB. And so what does that look like? So standard V2 is going to be a minimum for an unintended portable piece of equipment. When we're asked for FR materials, the assumption generally is that you're looking for a V0 material, but we do make sure to try to clarify that when being asked. So we make sure we're getting you, the right flame rated material, but standardly when someone says it's an FR material, normally they are referencing V0. And then a more stringent test would be your 5VA, 5VB. So these are conducted on plaques. I have pictures on the next slide to show you. But 5VA is going to be typically the minimum needed for an unintended permanent mount piece of equipment. So it's going to have that 5VA rating if you're going to use it for that piece of equipment. So some of the pictures, so we mentioned the horizontal burn, it's going to be held horizontally, and then the flame is down here on the side. So this is what a horizontal burn test looks like. Your vertical burn, V0s, V1s, V2s, it's held vertically fire is down here. As you can imagine, it's more stringent from being held with the fire underneath it versus over to the side. And then last but not least is your 5VA testing, 5VB testing. So it's put right under the center of the plaque. And so specifically, what does those mean? What do they have to meet? I do have a table on the next slide for you. So when you see something that says it meets HB or the V2, 5VA, 5VB, what does that mean? I'm not going to go through the whole table for you, but just note that your HB, it has a certain amount of time before it needs to go out. Your vertical tests have a certain amount of time it's allowed to continue to have the flame present before extinguishing. And then also specifically for V testing, vertical testing, they do have cotton underneath. So certain ones are allowed to ignite the cotton, some are not. So your V2 can ignite it. Your V1s and V0s cannot. And then the amount of time that it's allowed to continue to burn is a lot less with your V0 compared to your V2s. And then your 5VAs and 5VBs, very specifically speaking, we're looking at that plaque again on the last page. Your VA is not allowed to have burn through, and your 5VB can allow it. So we put it right underneath there. If it burns through it, you're getting 5VB. If it does not, 5VA. And so, like I mentioned, the table will be here if you want to review it in the future, but just note that that's what we use when we're talking about those different characteristics and the different ratings. And then if you're looking at specifically your Ultem data sheet, you can see the flame rating under flammability. It's got a V2, a V0, and 5VA rating. The other thing to also consider is when you do these ratings, they're based on thickness. So I might have, in this particular case specifically, at 0.4 millimeters, my Ultem's a V2 rated material, and so it's going to perform not as well as when it's 0.75 millimeters. So that's going to be a V0. So something to consider when you are asking for a specific flame rating for your material, do make sure to mention what thickness you need, because it doesn't do anyone any good if you have, let's say, a 0.5 millimeter part and you need to be V0. Well, if I'm making it out of this Ultem, the Ultem's not V0 until 0.75 millimeters. So at 0.5, we're not going to have the rating you're looking for. So it is something that it's good to know the flame rating and what you need and what's expected, but you also need to understand what would be the thickness of your part so we can make sure that we're matching that specifically to your needs. Another couple quick explanations, your transmittance and your haze. These are for your clear materials. So how much light are we allowing to pass through it would be your transmittance. So I gave a couple examples here. Your PMP materials is going to be 94, lets a lot of light through. Your PCs standard would be about 90. Your SANs, 88s. So just a couple different values for those ones there and what's expected. And then your haze value is how much is it going to scatter in a certain degree. So you could use this for stuff like diffused materials. So if you are looking maybe at PCs, maybe headlamps, and you want to be able to see all the light bulbs through it, you're going to want a really low haze value. You want the light to kind of just go through and not be scattered at a different angle that it's coming in at. If you're looking at something where maybe you'd prefer to be able to just have a white glow and not see any of the bulbs, you're going to look for a higher haze value. It's going to give you more of a diffused look, and it's going to give so you're not able to see the light bulb. So those would be some of the different tests that you would look at for that specifically. And then your refractive index is also something to look at. One thing to consider for this particularly is when clear materials are added that have different refractive indexes, you get to the point where if you're adding maybe a PC with a polystyrene general purpose, because of their refractive index differences, you might start to get more of a hazed appearance, or it might appear maybe like contamination. Just note that if you're going to use clear materials, you're going to want to use ones that have similar refractive index. If not, you're going to start to get what would be considered, haze or what looks like more of contamination. And so with that, that's kind of all the different properties we had. I left a little bit of time for questions if anyone had them. Like mentioned, there is a question section to enter your questions. I've also included my contact information if you wanted to contact me after the fact and had other specific questions that you wanted to talk about specifically. My email address and my phone number are there that you can call or send me a note, and I'd be happy to help. And then at this time, I'm going to turn it back to Jason if he had any questions from the audience that we can address at this time.
No questions so far, Andrea. We'll give everybody another minute or so to enter any if they have some, and then I'll give it to Sherry to wrap up.
And once again, we would like to just remind you, if you would like to download the handouts, now would be the time to do so here before the webinar ends. Once the webinar is completed, you will receive in about an hour a certificate of completion. So hopefully that will give you some credit with your HR department, and you will receive a full recording of this webinar as well. Even if you registered for this webinar and if you weren't able to attend, so that you know for future ones, you would receive a copy of the recording as well. And it doesn't look like we have any questions, so thank you, Andrea. Oh,
Oh,
there
we
is
do have
one
one
there. Go
question.
ahead, Jason.
A few, Andrea, I'll just read them off to you here. Is fatigue addressed in any material properties on the data sheet?
I would say not specifically. They do have different fatigue information that you can get, but generally it's not a property that you're going to see on data sheets. It's separate testing that has to be done. So not something you're going to typically see on a data sheet, no.
Yeah, I'd say if you have any requests or needs for fatigue data, reach out to us. It's generally, at least in most instances that we've seen, not readily published info, but due to our many supplier relationships that we have and historical files, we may have some on hand already to help you get to where you need to be from a data perspective, or we could work with the right suppliers or outside labs to determine how best to generate that data. So by all means, bring any requests to the table. Next question, Andrea, does UL 94 rating include certain electrical resistivity characteristics, or is it just flammability?
I would say if you're looking at RTI, that would be your electrical properties for it. But for specific resistivity, if that's kind of where the question's going, sometimes it is given on the UL yellow card, sometimes it's not. So like our bigger supplier for that would be the LMP line for their StatCon or Satelloy. Sometimes it's on the UL yellow card for it, but more often than not, it's tested separately and provided on a data sheet instead of the yellow card.
Thank you. Some materials like PEEK have viscosity value instead of MFI. Is there a way to compare both?
If you are going to compare them, you'd have to use the same test method and the same conditions for it. As far as a specific way to compare, like if one has for that material has melt flow and the other one has a viscosity test, either relative viscosity number, you're not going to be able to maybe look at them and just go, oh, I can compare that. You're going to have to look at the same values if you're looking at two separate materials. They're going to have to be the same test, same conditions.
Yeah, unfortunately, to Andrew's point, there's not really a great way to compare them. If anything, viscosity is a much more precise measurement, and it's going to, simulate the shear rate of an injection molding machine or extrusion much more pointedly. So, if we have viscosity data on hand for two materials, that would be your better comparison point. But yeah, unfortunately, can't really translate melt flow index to viscosity. Next question, Andrea, is are the melt flow values over load? Are they linear, so different material flow rates can be compared in real world? I can jump on that one. Generally, given that the rate of the test and the loads are so low and unidirectional, it's pretty difficult to compare it to the real world. Flow rates of any material. So to Andrea's earlier points about comparing ABS to ABS, obviously if they're measured at the same temperature and load conditions, we know that a 10 melt ABS is going to flow better than a 4 melt. A 20 melt is going to flow better than a 10 melt, but it's not nearly as scientific as we would prefer when we're trying to figure out how much extra flow is going to be needed to maybe fill out a part or get us through a thin wall section of the part. So it's great for comparing material to material as long as they're the same or similar polymer type, but outside of that, we don't draw too many conclusions on real world flow data from melt flow.
Jay, it looks like we have Tom White with his hand up here, so I'm going to try to unmute him. And Tom, if you have a question, You are unmuted if you want to go ahead and give us your question.
Okay, thank you. I was really just curious about two things. One, can you review how to download this presentation again? I must have missed that.
Yep, if
That's
you go to
question.
the handouts section, which is right below questions, you'll see 2 PDFs, and you should be able to click on those and download them.
Where is that?
Right here right below where in your toolbar, if you
I
look
don't have
down,
a toolbar.
Oh, are you online or are you just on the phone?
I'm online and the phone.
Okay. Well, there should be a section there for handouts, but if you can't see it, I will be happy to email these to you after the webinar is all done.
Okay. I already sent you an email about it. So, okay. All right. That aside, here's my question. It's hard to ask. Hopefully you can figure out what I'm trying to say here. But let's say I'm comparing two data sheets, and let's just pick tensile strength, for example. And I know one material works. It's used in the application today, and I'm trying to make a recommendation for, say, maybe a lower price material or a different material to my customer. And I've always operated with, the margin of safety. If one material works and its tensile strength 100, let's just say, I want to get within 10% of that number. And if I get 10% lower, or even higher, I know I'm in the safe zone. Is there a rule of thumb like that is actually science-based, or in your experience based, or am I completely out to lunch on that?
I would say that the 10% is a good rule of thumb, and that kind of stems from what is allowed as variation lot to lot. So you'll see plus or minus 10% is pretty standard for lot to lot variation. So if you're looking at a particular value, that's a really good rule of thumb to use. And so if you're, like you said, if you're looking at a particular material, it's got 100, that works. If you're within the 90 to 110 range, I would expect it to perform pretty similarly, because you're gonna get the same variation lot to lot for that material you're already using.
Okay. But let's say you hit 20% low, am I in the danger zone, or am I just in the suspicious zone?
I would say it probably depends on the application itself. If you feel like in the application you're getting kind of close to maybe the performance, and you're maybe seeing that it's getting kind of close to where you don't want it to be, I would say that's something to look at and to be aware of. The hard part here that we try to capture is that it is difficult to compare real world to the properties on the data sheet. So it is nice if you already have one that's working for you and that's working. We'd prefer to stay in the plus or minus 10, but if you're trying to cost save and maybe it makes sense, something that you could sample it, depending, like I mentioned, kind of depending on how it's performing for you. If you feel like maybe it's a little overkill or it's just right, that would push me more towards one or another, versus if it's plus or minus 20%.
Yeah,
All right.
I'll add to that, Tom, not to put too much nuance on this, but 20% probably is getting towards the realm of discomfort for me, at least. What we would want to reference, if possible, is to try to move away from even the data sheet values and see if we can get certification values, C of A from a certain lot, to show what actual testing performance would be consistency wise, rather than just what's on a data sheet. I love all of our suppliers, but as Andrea said at the start of this, they are marketing tools to a certain extent, so we don't want to use them as necessarily always real world test values. Is that the min, max, or average value that's on the data sheet? We don't necessarily know. The other thing that can massage that percentage difference is if we move away from tensile strength, say, and we look at something like modulus values, that basically measures the slope of a stress strain curve, and where in the test strain rate that's measured can greatly affect your modulus reading. So what may look like a 20% difference modulus, if they're just measured at two different areas of that peak, could be the same exact material functionally. So it kind of comes down to what tests we're comparing as well.
I see. Can I slip in one more question?
Of course.
Okay. You may or may not be able to answer this, but let's just say you are molding a part with a hole molded into the part, and that hole was dimensioned per a thread cutting plastic screw manufacturer's specification. So in other words, you molded a part, the hole is properly dimensioned size for the screw you're going to put in there. Mm-hmm. What property on a data sheet would best predict success for that screw holding, not pulling the threads out? Would that be flex mod?
Probably not. Well, that's a tough one to simulate. It would really be most likely a combination of your elongation value, which technically your thread cutting is going the opposite direction of a tensile test, right? Where you're pushing rather than pulling, but we can draw some similarities from it. So I would be looking at your tensile testing results more so than probably anywhere else in the data sheet. But when it comes down to thread cutting screws, you get into really the ductility of the polymer and how likely it is to deflect rather than fracture. And that's where elongation can be a good indicator. It's not going to tell you exactly what's going to work and what's not going to, but it will help you understand which material might be more forgiving than others.
Okay. See, those are good points. I reached out to the thread cutting screw guy for this problem, and he said basically ductility is where it's at, and the value from a data sheet that's most likely to at least sneak up on that number and give you some idea is flex modulus. So I thought he was off on that, and I thought it was more of a function of interplay between tensile strength and basically how ductile the material is, but I didn't know which property indicated that. Long story short, we ran a bunch of different materials, and lo and behold, the one with the highest flex modulus smoked the other candidates. So I don't know if he got lucky, or in a sample of 4 candidates, that just how it worked out. I'm not sure. So
sure.
I'm curious what you thought.
Yeah, for retention, rather than just avoiding fracture during the screw installation, so to speak, generally a stiffer material should retain a screw better, right? So if you're looking for higher pull-out force, yeah, that would make sense that flex modulus would be a good indicator.
Well, I was thinking that when the threads are cut, the material needs to get out of the way and not break when the major diameter is cutting, and then the material needs to creep back in around the minor diameter to create more volume of plastic around. So then that little bridge, so to speak, of plastic then is being pulled against. So the stiffer, the stronger, the higher tensile, et cetera, that piece is the better it would perform. And that was my theory, but
yeah,
turned out
I'd agree.
Yeah, but it turned out the material that was the most ductile had the highest flex mod, or the lowest flex mod, worked famously. And it was basically the test was you'd screw the screw into a certain torque, which was real low, wasn't high, but then you forced the part apart using they have a test machine. I think it uses air, and it tries to push the two apart, and it would pull screws out if the material was didn't have the low enough flex mod.
Gotcha. Understood.
I thought it was strange. But I appreciate your input. Thank you.
Yeah, no problem. I know we're over the hour mark here. We got a few more questions that we'll continue to answer, but feel free to obviously jump off as needed. Andrew, the next question is, can we always associate the difference of melt flow with the degradation of the material?
You can, yes, in the case of if you're taking it. So the reason that we do that is you'll take the melt flow of a material in pellet form right before you mold it, and then right after. Because what will happen is if you're putting too much stress on it, too much shear, you're going to start to break apart the chains. And so your material is going to start to flow easier. So if you're looking at something where maybe in the beginning, your PC, it ran at a melt of, we'll say 10, and then all of a sudden it's running at a 30, there's a high likelihood that within the processing, the chains are broken, it's flowing easier. Now, the other thing to consider that we did mention is if you're working with materials that are that are going to pick up moisture. If we're looking at maybe a nylon before, just depending on where the value was, how dry it was, what it was testing at before processing the melt flow there and then the melt flow after, that's something we're a little more leery of. But generally speaking, if you have a huge jump in melt flow, something's happening to where the chains are not as long, they're flowing easier. And so likely a problem with the processing.
Agreed. Next question is, different materials inherently react in different ways due to molecular composition, but are there any standardized test methods for UV and chemical exposure resistance on a TDS?
I would say typically not. You don't standardly see those tests on it. There are other tests that can be used, separately. So you can see UV exposure and your xenon arc test data. You can get stuff like that. They do it a lot for automotive. They do it a lot in other ones. So there's really not a standard one, and you're really not going to see it on your data sheet. But there is data available separate that we can try to get. But essentially it comes down to if it's been tested in xenon arc, and then a lot of times it's done based on color shift after the fact. So it started at whatever color it was the delta E and change after exposure. The other thing they could do too is sometimes they'll do maybe some physical property testing. So testing beforehand, exposure, and then the testing after the fact. I think there was another part of that, UV and chemical.
Yeah.
Sometimes, so chemicals, they do a whole assortment of different tests. A lot of times, if we can, we'd prefer to get the test results all from the same maybe lab or same guide, because then it should have been tested, all the same. Guides that we have from suppliers like Sabic, they will take the tests and they'll do some physical properties testing, then they'll put it a different strain and see how much cracking they're getting. There could be stuff like if you're using TPEs and you do chemical exposure, how much swelling there was. So there's a few different ways they do it. You're going to want to, if you're comparing materials, to look at if they're tested similarly for method and or the result at the end. So if one was swelling, check to see that the other testing was done to show swelling. If it's done in UV, try to make sure it's the same method or energy, and then same testing before and after the fact. But you won't see that on a data sheet. It'll be separate.
Thank you. Referring to shrinkage ratio, how is it affected considering different percentages of glass fiber content? And is it also affected by which place the gates are located?
The answer is going to be yes. So as we kind of showed in the one slide, your flow and transverse direction. So when you start to have materials that are filled with glass fibers, in the flow direction, the fiber will start to align. So you're going to have alignment of your fibers. And so when you look at the shrinkage in the flow direction, the glass is kind of going to be there to kind of hinder the shrinkage that's going to be allowed, because it's going to kind of stop the polymer from moving. And so that value is going to be smaller and less than in the transverse direction, where it's going to shrink more like just the standard polymer itself, because the fibers are not in line and hindering it from shrinking. So when you see values for like a glass filled material, you're going to see your flow and transverse flow properties. The one in the flow direction is likely to be, it's not going to shrink as much as transverse. And that's across any type of fiber that has an aspect ratio. So if it's longer compared to its to how round it is in diameter, you can get around that with stuff like your mineral fillers, because they are more spherical in shape, so they're not going to hinder the shrinkage in the flow direction like your glass fibers will. And so also because of that, then where you gate it is going to affect it. So if you gate it in the center of maybe just a rectangular plaque, your flow direction is going to be different than if you gate it at the end. So it really has more to do with where the flow direction is going to be and how those values are going to look based on that. And then the other thing too is also to consider that different materials already are going to shrink more or less, and then the glass is going to affect that even more. So if you're taking like an unfilled nylon and then you're adding the glass, it's going to shrink, but two of them are going to shrink quite a bit differently.
Awesome. Thanks, Andrea. Looks like that is all the questions we have.
All right, great questions, everybody. Thank you, Andrea, for your comprehensive presentation. Once again, if you, hopefully you can see the handouts. If you click on the PDF, it should download it into your screen so that you can open it up and save that. However, if you're having problems with those PDFs, just shoot me an email and I'll be happy to send those to you. So at this time, we would like to thank you all for taking time out of your busy schedules to attend this Chase the Knowledge webinar. We hope it was informative and a great return on the investment of your time. Once again, we would greatly appreciate your feedback through the survey you will receive shortly. And if you have any technical questions that did not get answered today, feel free to reach out to Andrea directly. Her information is posted on your screen. Thank you all for attending and stay well.